So this is joint work with Anne Broadbent on quantum homomorphic encryption for circuits of low T-gate complexity. So in the classical cryptography setting, homomorphic encryption, an idea which has been around for decades, asks for a functionality that seems at first like it might not even be possible. We want some means of encrypting a message X such that we can evaluate any function f on the encrypted message without being able to decrypt or learn anything about X. So we want to be able to take an encryption of X and turn it into an encryption of f of X. And it wasn't until 2009 when Gentry gave the first fully homomorphic encryption scheme, allowing any classical message X to be encrypted in such a way that any function f could be applied to X without decrypting. But of course, we know that this isn't really fully homomorphic encryption because there are many other things that we could do than applying just a classical function. I'm going to be talking in my talk about quantum homomorphic encryption, which generalizes this classical idea in two ways. So first, we want to be able to encrypt an arbitrary quantum state, and we want to be able to then evaluate any quantum circuit C, which implements some quantum channel, on the encrypted quantum state. So we want to be able to turn an encryption of some quantum state rho into an encryption of a quantum state that we would get from applying a quantum circuit C to rho. So for instance, if I wanted to delegate the factoring of some integer, but I wanted to encrypt this integer, and I want to give this to some server to factor for me homomorphically, this would already be possible using, for instance, Gentry's fully homomorphic encryption scheme. We would just have this function f would be some classical circuit for factoring. But then this would be a super polynomial-sized circuit because we don't know of any polynomial-sized classical circuit for factoring. And so this evaluation procedure would necessarily take super polynomial time. Whereas with quantum homomorphic encryption, I could ask a server to homomorphically evaluate a quantum circuit for Shor's factoring algorithm, which would be a polynomial-sized circuit. Okay, so I'm going to start by defining formally what I mean by homomorphic encryption scheme. So I'll start with a classical case. A classical homomorphic encryption scheme is four polynomial time randomized algorithms. The first is a key generation procedure, which takes some security parameter kappa and outputs 3 keys. So there's an encryption key, an evaluation key, and a decryption key. Then there's an encryption procedure, which takes an encryption key and a message and outputs some ciphertext. Then there's an evaluation procedure, which takes an evaluation key and a ciphertext, as well as some function f, which we describe by some circuit in some universal classical gate set. So for example, a circuit consisting of addition and multiplication gates. And then the evaluation procedure outputs another ciphertext, C prime. And then finally, a decryption procedure takes a ciphertext and a decryption key, and it outputs a plain text, which we hope is the result of applying f to the message m. So in the public key setting, we imagine that Alice would generate some keys, and then Bob would use Alice's encryption key to encrypt some message. And then he would give the ciphertext to Charlie, who could homomorphically evaluate some function f on his message. And then Alice should be able to decrypt the result and get f of m. And in the symmetric key setting, we would just have Alice generate keys as well as encrypt. But we'll consider the public key setting for now. And we would like such a scheme to have certain properties. So we would like that it actually is homomorphic for some function, so it should have some kind of correctness. So we say that a homomorphic encryption scheme is C homomorphic, where C is some set of classical circuits. If for every circuit f in C, we can homomorphically apply f. So that means that if Charlie inputs f into the evaluation procedure, when Alice decrypts, she actually gets f of m. And so before, for instance, the first fully homomorphic encryption scheme, there were homomorphic encryption schemes that only worked for some limited classes of circuits, like circuits of low depth. We would also like this scheme to be secure, because it is a crypto system after all. So we want that an encryption of a message m actually hides m, or more specifically, we use the sort of standard cryptographic security notion of indistinguishability under chosen plaintext attack. And this basically just says that no polynomial time adversary should be able to distinguish between an encryption of 0 and an encryption of 1 with non-negligible probability. And there's one final property that we would like. To motivate this property, let me describe how we can very trivially get a scheme which is secure and homomorphic for all circuits. I call this the trivial scheme. So we fix any public key encryption scheme which is in CPA secure. So this consists of a key generation procedure, an encryption, and a decryption procedures. And our trivial scheme is going to be as follows. So our key generation procedure is just going to call the public key scheme's key generation procedure. And this just outputs an encryption key and a decryption key, and we're not going to need any evaluation key. So next, our encryption procedure is just going to call the public key scheme's encryption procedure. So we're just going to encrypt the message M with this public key crypto system. But the public key scheme doesn't have an evaluation procedure. So our trivial scheme, to evaluate some function f homomorphically, it's just going to concatenate the ciphertext C and the circuit f and just output the pair of these. And then to decrypt, we're just going to use the public key encryption scheme to decrypt C to get M, and then apply f to M to get f of M. So this is secure as long as the public key scheme that we started with is secure, and this is homomorphic for all circuits. But this is clearly not what we mean by a fully homomorphic encryption. We've cheated by pushing all of the work of evaluating f into the decryption procedure. We've done no work in the evaluation procedure. So the final property that we require is compactness. The complexity of decryption should not depend on the evaluated function f. So we shouldn't be able to just push all of the work of evaluating f into the decryption procedure. It should all be done in the evaluation procedure. And so a scheme which is compact in CPA secure and homomorphic for the set of all classical circuits is called a fully homomorphic encryption scheme. And a quantum homomorphic encryption scheme is very similar. Now we have 4 polynomial time quantum algorithms. So again, we have a key generation procedure, and in our schemes we allow the evaluation key to be a quantum state, and our encryption key and decryption key are just classical, but that's just because we don't require any quantum encryption and decryption keys for our purposes. We could also have allowed those to be quantum. So now we want the encryption procedure to encrypt some quantum state, rho M, and so it's going to output a quantum cipher state on a system C. And we want to be able to evaluate a quantum circuit. So this is just a classical description of a quantum circuit in terms of some universal quantum gate set. And we want the decryption procedure to output a quantum state, which should be the results of applying the quantum circuit C to the quantum message rho M. And we require similar properties. So we say that a scheme is Q homomorphic, where now Q is a set of quantum circuits. If for every circuit C in Q, we can homomorphically evaluate C. And this just means that the output of decryption should be close in terms of trace distance to the result of applying the circuit C to the initial message state rho M. And we define a quantum version of indistinguishability under chosen plaintext attack. This is our notion of security. And essentially it says that no polynomial time adversary should be able to distinguish an encryption of a state rho, where rho is chosen by the adversary, from an encryption of a maximally mixed state. And finally, we also have the property compactness. The complexity of decryption should not depend on the evaluated circuit C. Okay, so now I can talk about our results. So we don't achieve the full functionality, but we achieve some sort of partial results towards full quantum homomorphic encryption. First, let me talk about some prior related work. So there's been a number of different works looking at secure delegated quantum computing. And this is where there's some server, some quantum server, and you want to delegate your quantum computation, but you want to have your input encrypted so that the server doesn't know what your input is. And sometimes these also hide what computation is being performed. And the main difference, although we use a lot of techniques from these works, our works build on these, but the main difference is that our work does not involve any interaction between the person who encrypts the input and the person actually evaluating. So that's one difference between just delegating your computation and actual homomorphic encryption is there's no back and forth interaction allowed between the encryptor and the evaluator. So it was shown in 2014 that quantum fully homomorphic encryption is not possible with information theoretic security. So this sort of justifies our use of computational assumptions. And finally, there has been some study of quantum homomorphic encryption in a very different security setting. This is a very different setting than our work. So Tan et al. Consider quantum homomorphic encryption where they bound the amount of information leaked. So they don't have any computational assumptions, unlike our schemes, but they also don't achieve cryptographic security. There's no semantic security in their scheme. Okay, so before I state exactly what we achieve, let me briefly compare quantum and classical circuits. So classically, addition and multiplication form a universal gate set, and addition is typically the easy gate to implement homomorphically. So if we want to consider classical homomorphic encryption, it's sufficient to consider how can we homomorphically add two ciphertexts and how can we homomorphically multiply two ciphertexts. And in all of the fully homomorphic encryption schemes that exist, adding is very easy. You just add the ciphertext, and that gives you a ciphertext that encodes the sum of the two messages. Whereas multiplication is always a much more involved procedure. So in the quantum case, we of course have a number of possibilities for universal quantum gate set. So we start with the Clifford generators. So that's the Hadamard, phase gate, and a control NOT gate. So these generate the Clifford Group, which is a special set of quantum circuits, which includes linear circuits, which are those generated by addition, but it does not include the ability to do multiplication. So Cliffords really, in a number of ways, are analogous to classical circuits that are generated by addition gates. And then to get a universal quantum gate set, we know that it's enough to add any non-Clifford gate. And we choose the non-Clifford T gate, which is a standard gate, and it's the square root of a phase gate P. But we could have chosen any non-Clifford gate instead of the T gate. This would give us a universal gate set. So this is the universal gate set that we look at. But another choice that we could have gone with is instead of a T gate, we could have used Toffoli, which is a reversible multiplication gate. And Toffoli and T gate are very much related. And for our results, you should really consider a T gate to be kind of the quantum analog of a multiplication gate. And as we will see, we can actually get a scheme that is homomorphic for Clifford circuits from any classical scheme that's homomorphic for linear circuits. So they really are analogous. And the T gate, like the multiplication gate, is going to be the hard gate to implement homomorphically. Okay. So we do not achieve quantum fully homomorphic encryption, which would be homomorphic for all quantum circuits, compact, and QCPA secure. But before I say what we do achieve, let's look at what we could do trivially. So by not encrypting, we get a scheme which is homomorphic and compact, but has absolutely no security whatsoever. As I mentioned before, the trivial scheme is homomorphic and secure, but it's not compact because the complexity of decryption scales with the number of gates in the evaluated circuit. And something like the quantum one-time pad, where we encrypt a quantum state, this is not homomorphic at all, but it is compact and secure. So it's easy to achieve any two of the three properties. So we achieve some partial results that are better than these trivial results, but don't quite achieve quantum fully homomorphic encryption. So we start with a scheme which is homomorphic for Clifford circuits and compact and QCPA secure. And then our other two schemes build on this first scheme. So the second scheme uses auxiliary states, so we call it aux. And this is homomorphic for quantum circuits with arbitrary Cliffords and only constant depth in T gates. And this is compact and secure. And then our third scheme, which also builds on the first scheme, is homomorphic for all quantum circuits, but it is not compact because the complexity of decryption scales with the number of T gates in the evaluated circuit. but it is secure. And I'll also just mention our first and third schemes are public key, whereas our second scheme is symmetric key. So in the rest of my talk, I'm going to present our first scheme, the Clifford scheme, which is quite simple, and we can start with any classical encryption scheme that's homomorphic for linear circuits and turn it into a quantum scheme which is homomorphic for Clifford circuits. Okay, so let's just review the Pauli group. We have this very important gate, the X gate, which is just a classical NOT, and the Z gate, which just maps plus to minus and minus to plus. And I'll be using this notation for any n-bit string A. The Pauli group is just essentially for every n-bit string A and B, x to the A, z to the B, for some phases which are not important. And we know that if we choose a random Pauli and apply it to a quantum state, this is the quantum one-time pad, and this is information theoretically secure. Okay, and the Clifford group, of course, is the normalizer of the Pauli group. So this means that for any Clifford C and any Pauli x to the A, z to the B, there's some other Pauli x to the A prime, z to the B prime, such that this identity holds. In terms of circuits, that means if we apply any Pauli followed by a Clifford, it's the same as applying that Clifford followed by another Pauli. So for every Clifford C, there's some function, f sub c, that satisfies this relation. And it's not obvious, but this is actually always a linear function. So for example, this identity holds up to some global phase for a phase gate P. So we write f sub p of AB equals A plus B. Okay, and we only need one final ingredient for our first scheme, which, as I mentioned, is some classical homomorphic encryption scheme, and it actually only needs to be homomorphic for linear circuits. Okay, so our Clifford scheme's key generation procedure we'll just call the classical key generation procedure. And then to encrypt, we're just going to apply the quantum one-time pad. So choose random A and B and apply x to the A, z to the B, and then encrypt A and B with our classical encryption scheme. And then to evaluate any Clifford C, we're just going to apply C on the quantum state. And then because of this identity, C x to the A, z to the B equals x to the A prime, z to the B prime C, we know that we now have an encryption of C applied to our initial state, but the encryption now has different one-time pad keys, A prime and B prime. And so we're going to homomorphically evaluate FC on our encryptions of A and B to get encryptions of A prime and B prime. And then to decrypt, we just decrypt to get A prime and B prime, undo the quantum one-time pad, and this leaves us with the Clifford C applied to our initial state. Okay, so this is homomorphic for all Clifford circuits, and it's not easy, it's not difficult to see that it's compact and secure. And then I'll just mention, to get our second scheme, we use auxiliary states to implement T gates, but for depth L in T gates, we need n to the 2 to the L states, so this only works for constant T depth. And then for our third scheme, we use entanglement to delay part of the T gate evaluation, which results in the scheme not being compact. Thank you.
Thank you, Stacey. Questions? Yes?
Hello. I was just wondering if there's a way to compare different schemes, like in terms of the size of the secret key or something like that. Like, for example, you mentioned that there are previous works that use interaction, but this one doesn't, right? But is there a trade-off? Like, does this do worse in some other way compared to those? In other words, does interaction help at all? If this is just as good as the ones with interaction, then you might as well not use interaction, right?
I see. I guess it depends on your goal. So I think that the schemes with interaction, like the most recent scheme, might be better in terms of the abilities that the client needs to have in terms of like the quantum computation they can do. So if your goal is just to delegate computation and you're fine with interaction, then I would say probably the schemes with interaction might be better, but they wouldn't qualify as homomorphic encryption. So they do require that you kind of are constantly in contact with the server, which you might see as a downside.
Okay, so one more question.
Okay, so in your Clifford encryption scheme, you mentioned you need public key, while for the other scheme you need maybe symmetric key. Can you explain why there's such differences?
Yeah, so I guess in the symmetric key scheme, we provide auxiliary states, and these states depend on all of the secret key that will be used, and they need to be provided sort of ahead of time. And so this can't be done in a public key way. So it's because of like providing these auxiliary states, which depend on all of the secret key.
Okay, let's thank Stacey again.